ঠিক আছে হবে
এইটো এফালে নিব পাৰিব নি So very good morning everyone.
ক্যামেরাটা এইটু ক্যামেরা চলে আছে
So in this lecture, before moving on to the hands-on session, I'll be briefly talking about what is hydrological modeling and what is basically why we use the hydrologic modeling, how we simulate some rainfall runoff model and how to calibrate the model, and a brief introduction to the HEC HMS model. So in this slide, what we see here, this is our planet Earth, and what we can see, which color is predominant in this particular image. This is the blue in color. Then why blue color? Blue color what indicates?
Water.
Then water. Then what does it mean? That a major part of our Earth is covered with water. So when we see the distribution of water, we can see that 71% of the Earth is covered with water and only 29% is land, and out of that 71%, again 97% is marine water. So if it is marine water, then you have more dissolved salts and that is not fit for drinking. Then only 3% is left as fresh water. So again, this is fresh water, that means it has less dissolved salts and it is fit for drinking. Then out of that 3%, we can see glaciers has 69% and groundwater 30%. And we are left with only 1% in rivers and lakes. So we focus on the surface water hydrology. So that 1% of water which is available in rivers and lakes. Now what is hydrology? Hydrology is simply the study of water. Distribution of water, its occurrence, its physical and chemical properties, then its interaction with the environment. So this is called hydrology. Then when we studied hydrology, say in our BTech, so what is the basic term we studied in hydrology is this hydrologic cycle. Then what is hydrologic cycle? Simple. Clouds, rain. What clouds, rain?
Evaporation.
The first thing in the hydrologic cycle is your evaporation. So water from the oceans, it will evaporate due to the heat energy provided by the solar radiation. Then the water vapor moves upward, condense and fall as rainfall. However, some of the clouds, it will be moved to the landmass by the wind, and there it will condense and fall as a rainfall or precipitation on the ground. So while falling on the ground, what happens? Before falling on the ground, there is one term, it is called interception. So interception may happen. Interception means the water is intercepted by the vegetation or other structures. Then rest of the water will fall on the ground. Then what will happen for that to that water that has been fallen on the ground? Yes. Infiltration हो जाएगा और क्या हो सकता है? Surface runoff से पहले और भी कुछ होगा. There are some losses. Yes, मतलब surface में depression होंगे, उसमें water storage हो जाएगा. Infiltration, there will be infiltration, and then also transpiration. So evaporation and transpiration. So in combination, we term it as evapotranspiration. So whatever water is left after all these losses, it will be our surface runoff. Then after that, it will again flow to the streams. Then from stream to the lakes, stream to the oceans, and the cycle will repeat. Again, the evaporation will occur. So this is a natural cycle. This is the water cycle. So this is just one animation showing the water cycle, how evaporation is occurring and all this. Now, from the water cycle, what are the main components we have identified? First, evaporation will occur, then condensation. After condensation, there will be precipitation. When it is falling on the ground, then infiltration will occur. There is another term, percolation. So, anyone, can you say what is the difference between infiltration and percolation?
परकुलेशन को होता है जब वाटर मूवमेंट हो रहा है नीचे डाउनवर्ड वाटर लेवल को टच कर जाए और इन्फिल्ट्रेशन में क्या होता है वो किसी ऑब्स्ट्रक्शन की वजह से वो वाटर लेवल को टच ना करे
नहीं टच नहीं कर पाएगा ऐसा नहीं है इन्फिल्ट्रेशन मींस whenever water is falling on the ground, the first thing the soil is absorbing the water. Okay, that is called infiltration. That infiltrated water will move for percolation. Infiltrate होगा water वही जब deep down होगा. First initial term को हम infiltration बोलेंगे. The rate at which the soil is absorbing the water. जब infiltrated water नीचे जाएगा, then it is called percolation. Then transpiration and runoff. So these are the 5 main components of hydrologic cycle. Now we have understood what is hydrology, what are the different components of the hydrologic cycle. Now what is hydrologic model? So say all these components for the water resource planning and management and sustainable development of a region, we need to study all these components of the water cycle. And what is the how we can identify all these components? For that, hydrologic model has been developed. So hydrologic model is a mathematical equation which represents real world problem. So it comprises of 3 components: input, operator and the output. You have the input, you give the input to the system and it will get the output. So it's a computer model that simulates various components and functions of the hydrologic cycle. So hydrological system and their underlying processes are complicated. So hydrologic models and model is considered adequate if difference between model prediction and measurement is small. So what does it mean? Means when we run a hydrologic model, it will give some output. Say we are giving rainfall as the input, then it will produce runoff as the output. So this is the model developed output, the simulated one. Then if we have the observed data, then we can compare whether the model is functioning well or not. So a model is considered to be adequate if the difference between the model simulated runoff and the observed runoff is less or minimum. Now what are the basis for many hydrologic model? So this is a continuity equation. This is the fundamental equation for any hydrologic model. Input minus output is your change in storage. So this is a water system or a watershed. So what are the inputs? These are the precipitation is your input to the system. Then also groundwater recharge is another input to the system. Then what are the outputs different? Evaporation, transpiration. Then stream flow itself is an it is going out of the system. So parameters input minus the what are the outgoing parameters is your change in storage. So this is the basic equation that is to be considered in any hydrologic model. वो सॉफ्टवेयर वो करा दो क्या मैं दे दूं पेन ड्राइव है I think space नहीं है
और स्पेस नहीं जाओ
So while I am giving this lecture, in the meantime they will download and install the software in your systems. So in hydrological model, you have the input to the catchment input, then the model will run and then it will give the output. So this is the just a brief diagram. Now why we need the hydrologic model? First one is to understand the hydrological processes, then to estimate the individual hydrological components, to generate scenarios with respect to land use change and climate change, to manage water resources for the benefit of mankind. So the third point is important, to generate scenarios with respect to land use change and climate change. See, we have some present data, and with that data we will develop our hydrological model. Then we calibrate and validate the model, and if we see that okay, this model output is okay and the model is quite accurate, then that particular model we can be used for future generation of runoff. If we have the climate change data of future or meteorological data, then we can use that particular model to understand the future scenario of that particular watershed. Then there are different types of hydrological models. So based on like aspect of randomness, then process description, spatial and temporal resolution. So first hydrological model based on aspect of randomness, it can be a stochastic model or can be a deterministic model. So it can be a stochastic model and deterministic model. So what do you mean by a deterministic model and a stochastic model? See, it based on aspect of randomness. If it is a deterministic model, then there are some randomness involved in the model. That means, and if it is a stochastic, then there will be some probability. So, say for example, deterministic means, say we want to forecast something. So, forecasting is deterministic. That means you have certain values for forecasting. And if we say prediction, prediction is stochastic. That means there are some probability involved with the model. For example, say evaporation. We know the say this is the temperature for today's temperature. This is the pond area, and other some related features we know about it. Then we can determine the evaporation. What will be the evaporation from that particular pond today? So this is deterministic. We understand that this much value will be the evaporation from this pond. But if we want to predict the rainfall, so rainfall, I cannot say that exact value. So this is a prediction. There are some probability involved in that. So that means forecast is your deterministic. However, prediction is your stochastic, and probability is involved. Then based on your process description, there is empirical model, conceptual and physical. So empirical models, these are basically empirical models. These are the simplest model. These are based on some mathematical equations. So those equations have been developed from 30-40 years of experiments for a particular watershed. Then empirical model method you cannot use empirical method that has been developed for a particular watershed to another watershed. However, we are using the empirical models for different watersheds. In that case, we have to change the coefficients. There are some equation, there is some coefficient involved. For different particular reasons, the coefficient can be different. Say for example, empirical method, or also it is called a black box model. That means we don't understand what is happening inside the system. Only I am giving the input. The model will do something, black box, totally blank, we don't know what is happening, and the model will give the output. Say for example, today 100 mm rainfall is occurring, and I want to know what will be the runoff at the outlet. And say for that particular watershed, there is one empirical equation has been developed, like rainfall runoff is equal to 0.6 into runoff. So we have the value of runoff, rainfall as 100 mm. So what will be the runoff? 0.6 into 100, 60 mm will be the runoff. I'm just giving the value to the equation, and I don't know what is happening inside. What is the impact of land use and cover? What is the impact of other soil properties, all these things. So this is empirical model. Then the another one is your physical model. So this is the complete opposite of your empirical model. Why? Because here all the physical properties of the watershed is taken into consideration. Like all the physical laws of conservation of mass, momentum, energy, all these are considered in physical model. So this is cumbersome and however it gives a very accurate result. But as an engineer or as a scientist, we are not much interested in empirical model as well as physical model, because physical model is very, although it is very accurate, but it requires much skill, and this sometimes don't give the accurate result. So in between, we compromise with the conceptual model. So it has the properties of both the empirical model as well as the physical model. So it takes the physical laws, it considers the physical laws, but in a very conceptual manner. Then, depending upon the spatial resolution, the models can be lumped, semi-distributed or distributed. So if it is a lumped model, that means if I consider a watershed, the model will consider the whole watershed as a single unit. Okay? Whatever parameter I am giving say rainfall, one single rainfall value it will consider for the entire watershed. However, for then the second one is your semi-distributed. In semi-distributed, it will divide the watershed into some sub-watersheds, and for each sub-watershed, the parameter will be different. We consider the properties of each sub-basin. And the third one is your distributed model. In distributed model, it is even more complicated. It will divide the entire watershed into small grids, like square grids, and it will consider the parameters, properties of the properties for each grid. So it is distributed, and depending upon the temporal resolution, it may be event-based or continuous. So event-based means when we are considering one single event of a hydrograph, like the flood event. So when we are considering that on the, then event-based. Continuous means we are simulating the model for long period of time, like for 2 to 3 decades. So this is your continuous model. Then steps in hydrologic modeling. So first step is to delineate the watershed. We will be given one input. So it will be shown in the practical session. So then we will be having one outlet, and then first step is your delineation of the watershed. Then obtain the hydrologic and geographic data. Then obtain whatever data we have for that particular watershed. Select the modeling approach depending upon your objective, what model will be using. Then calibrate and then validate the model. Once the model has been simulated, we will have to calibrate the model to check its accuracy. And then use the model for assessment, prediction and design. Once the model is ready, we can use it for further analysis. Then hydrologic modeling system, this is HMS, which we will be using in our practical session. So this is again the your hydrologic cycle, and what HMS do, it provides different models or different methods for each of the component, and we'll be using that in our model. And then also it has the HMS has a rich graphic user interface. That means you can see your watershed, what are the properties, different properties, and different buttons will be there with the help of which you can enter your data and all these things. And this is how you can get the output. So HMS, HEC HMS. So HEC HMS, it was developed by Army Corps of Engineers through their Hydrologic Engineering Center. So Hydrologic Engineering Center, that's where the term HEC is coming, and HMS is your hydrologic modeling system. So it was the first version was developed in 1992, and it can be used for both small watershed to very large river basin, and incorporates range of hydrological concepts. So again, it's a mathematical model. It can be used as both lumped as well as semi-distributed. both event based and continuous, whatever model description I have described the slide before, and it uses the deterministic technique. So HEC HMS can do both as a lumped model, semi-distributed as well as distributed. Here one parameter is considered for the entire basin. Here the basin has been divided into like 4 sub-basins, and for each basin we will define the parameter, and based on that it will give the output. And here the entire watershed is divided into number of grids, and for each grid we will be giving the parameter value. And this is actually much very complicated, so we'll be focusing in this session this semi-distributed model. And then event and continuous. So the event and continuous I have explained already. So this is a event based model, so only one event is considered here. And here this is the, in the right hand side, this is the continuous model concept. This is the output, final output of a model. So here above it is the depth in inch, that means it is the rainfall, and this is the runoff. So see, in the event based model we can clearly identify the peaks, but it is getting difficult for the continuous model because we are considering a very long period of time for the simulation. Then GIS processing. See, GIS, you have already used geography information system like ArcGIS and all these things. So what HEC HMS does, you don't have to use ArcGIS separately. The GIS facility is incorporated in the model itself. So when you run the model, so first GIS processing, like when to delineate a watershed, we have to modify the terrain like fill, sink, flow direction, flow accumulation. All these things you can do in the model itself. Then sub-basin and ridge delineation, sub-basin and margin, sub-basin and ridge. Okay. Then we have to give the parameter values to the sub-basins and all these things. So when you open the HEC HMS interface, you will see like this. There are 4 compartments: watershed explorer, desktop, component editor, and then message log. So desktop is more like a map interface. So here you can see your basin and whatever process you have done in the GIS. So it is displayed in the desktop. Then whatever you have given, like this is a basin, so this is basin, then what are the sub basins, so all this information you can get in the watershed explorer, right? Then when you click something in the watershed explorer, the properties associated with that particular component or element is visible in the component editor, right? And when you run the model, if you get any error or whatever, you will see it in the message log. So these are the main 4 compartments when you open the HEC HMS software. Then above, these are the menu bars and then toolbars. Then when we create a HEC HMS model, you have to develop 4 different files. First one is your project file. Project files means just you create first the project. So this project file will have the extension of .hms, and it containing the basic information about the project name, what version you are using, data file name and time zone. Then second, we have to create a basin file. So basin file has the extension of .basin, and it contains the watershed's physical properties, stream network, connectivity, all these things. Like in the previous slide, I have shown you the basin. So this is the creation of the basin, and it will have all the properties of the sub-basins and what are the reaches, what are their properties. All these are there in the basin file. Then we have to create one meteorological file. So in the meteorological file, we have to provide all the meteorological information, like all the weather information, whether the rainfall, temperature, all these things we have to give in the meteorological file. And then finally we have to create one control specification file. So in the control specification file is the final element that we have to create in the HEC HMS model, and it has the extension of dot control. So I have the data, then I have to run the model from this time to this time. So all this information we will finally have to give in the control specification file. Then populating the basin file. So when we first, this is the first thing, the basin file. So when we first create the basin, like using the GIS interface of the HEC HMS, we will delineate the watershed. Then we will just delineate the watershed and the reaches, all these things. But we don't have any properties related to this. So first step is we have to delineate. Then the second step is to, we have different methods for different purposes in the hydrological model. So in the second step, we have to select those methods. And in the third step, for each method, we have to assign the parameters and parameter values. So this is, you will get to know when we will do the hands-on. And again, see, in HEC HMS, we will develop this GIS layer. But this is a computer system, HEC HMS, and it won't consider the shapes and all these things of the GIS interface of the watershed. So what does it do? It creates something like this. This is your schematic diagram. So these are the sub-basin. Okay, these sub-basins, these are the polygons, and it is designated as sub-basin 1, 2, and these dark blue lines are the ridges. So it won't, though it will be available, but in HEC HMS, the model only consider this schematic diagram. Then these are the icons for like sub-basin. It converts the rainfall hydrograph to rainfall hydrograph. These are the sub-basin. Then reaches, reservoir, junction will be there, reservoir, but we will be using only sub-basin, reaches, junction and sink. Sink is nothing but the final outlet. So these are same, the hydrologic elements. Then the sub-basin concept is very important in HEC HMS. See, sub-basin is where the rainfall is converted into runoff. So here the input is your precipitation. Okay. Then what will the model do? It will convert the precipitation into excess precipitation. What is excess precipitation again? Precipitation and then excess precipitation. You have the precipitation, then after satisfying all the losses, whatever is remaining, this is your excess precipitation, it will contribute to the runoff. So model will, I will give the precipitation as input, then it will convert it into excess precipitation. That means it will consider the losses due to canopy. Canopy means the intersection. Whatever rainfall is falling, vegetation is intercepting, so canopy. Then surface, that means surface depression and all these things. Loss means the infiltered water. So all these will be subtracted from the precipitation and it will convert the precipitation into excess rainfall. Then that excess precipitation will be converted into direct runoff. Then that direct runoff will be, from the that direct runoff, the model will produce the direct runoff hydrograph using some transform function. Okay, so direct runoff, after creating the direct runoff hydrograph for each sub-basin, it will be routed through the reaches to the outlet to get the final output. So routing, so we have the DRH or Q from the sub-basin. DRH means the direct runoff hydrograph from each sub-basin. Some routing operation will be there, and then we will get the final discharge. And in the routing, gain and loss will be there. So in the process, some water may be water may joint or some water may have lost, so gain and loss. So these are the commands available from the file menu, like you will see it itself in the practical session. So these are the commands available from different menus, like file menu, edit menu, then view menu, and all these things. So what I have explained, HEC HMS project model components are: the first one is your basin model. Then for the basin model, we will develop the sub watershed. We will give all the methods for different components of the water cycle and different parameters. Then we will create the meteorologic model where we will give the weather data, and then finally we will create the control specification file to simulate the model. Then there are different subbasin methods. Like for canopy, we can choose the method of our choice depending upon the properties of the subwatershed or whatever data we have with us. So these are different methods available for different components. Like for canopy, these are the methods. For surface, these are the methods. Then loss, we will be using SCS curve number method here. Then transform method is there, that is transforming the direct runoff to runoff hydrograph. So there are different methods. We will be using the SCS unit hydrograph. Then base flow. So these are the sub-basin methods. Then there are reach method. What is done in the reach? The routing operation is done in the reaches, that is the streams. So these are the different methods, and we will be focusing on the Muskingum method. So these are the meteorologic information you can give to the model, like temperature you can give, precipitation, wind speed, pressure, and evapotranspiration if you have those data. If it is an event-based model, then we don't need to give the evapotranspiration. But if we are using a continuous model, then evapotranspiration data is to provide evapotranspiration data is important. Then you will get the PPT. You need to take the photos. So 5 results display in HMS. So once you run the model, there are different ways you can view the results. So first one is your global summary table. So here, see, I have there are different rows for subbasin 1, 2, then reach 1, 2, whatever elements I have created in the GIS interface. All these are available, and the information for all these elements is there in the global summary table. Then second one is element graph. That means for each subbasin, for each reach, you will get the result, and this is for one subbasin. So here we will get depth versus flow. That means the rainfall versus the runoff. Then you have this element summary table. Then for each element graph, each element, you will also get the element summary table. For each subbasin, the table will be different. However, you will always get this peak discharge volume and all. Then you have the element time series. Whatever graph you have, the numerical display is, you can get the numerical display in the element time series. And another option is your spatial results. You can visualize the different elements like rainfall and all these things in spatial way. So we'll be showing in the practical. Then there are different 5 ways to access results, like results tab is there. Then these are the options, like first one is this is the interface. When you create all the components, you will get the result button here. From the result button, you can visualize the result. Then the second option is you have this GIS interface. You click on any watershed, right click, and then you can get the view results option. Then in the menu bar itself, you will get the results. So these are the different options you will have to explore. And then another option is your accessing the results using the HEC DSS file. So for that, we have to install HEC DSS view one software is there, standalone software. We have to install it, and then we have some file, DSS file. Then from the folder we can visualize the results. Then HEC HMS simulation types, there are different simulations. If I am going to explain it, it will be quite monotonous. So I will not explain everything. But these are some HEC HMS simulation types like simulation run. So basically the simplest one is your simulation run, and we will be using simulation run. And for calibration purpose, we will be using the optimization trial. So these are different methods. So just for simulation run, we have to create those basin file meteorological, then basin and control specifications. So simulation run is basically the combination of all these components. Then optimization trial, there are some algorithms for this method. We have to take some objective function, then some algorithm, and we have to optimize the model. So this is the optimization trial method. Then we have the forecast alternative. This is one simulation type. Here we run the model for one time period. Then based on that we can forecast the runoff or discharge. Then depth area analysis is there. For this we have to simulate the model for different locations. Then another one is your uncertainty analysis. So these are some different. Yeah, so these are some simulation types. So once you understand what hydrologic model is, what is HEC HMS, then we simulated the model. So our next step is to calibrate the model. So what is model calibration? There are a lot of slides. I will give you the presentation. I will not explain everything, but I will just simply briefly tell you what is model calibration. In the very beginning, I told you that when we run one hydrological model, we will get some results. So this is the model result. Okay, and it may not represent the true physical properties of our watershed. Then what is model calibration then? Say for particular watershed, for a particular gauge station, we have simulated the model. Now for that particular gauge station, we have the observed data that has been collected by some department, water resource department, CWC. So now in calibration, we will do some process. We will set some parameter and we will check whether the observed data is matching with the simulated data. So that process is the process is like trial and error method. So we will assign some parameter, we will try to change that value, and we check the calibration process is done. So there are different parameters available. Like for example, I am telling you one curve number. Have you heard about the term curve number? Curve number for a watershed. What does it mean? See, actually, it doesn't have any physically it doesn't mean anything, but you should understand that curve number when it is more, then there will be more runoff, and if the curve number is less, there will be less runoff. So if more runoff means when the runoff will be more, when the land is impervious. If impervious, then more water will be lowest runoff. So you can understand that if this is a higher curve number value, that means might be that surface is concrete or impervious, and if the curve number value is less, you will get less runoff. That means it will be a forested area because much of the precipitation is absorbed by the soil. So this is the concept of curve number. Mostly in calibration, we first focus on the curve number value. And curve number is always a combination. It's a combination of land is land cover, and hydrologic soil group. So hydrologic soil group, anyone? Sorry. Hydrologically, soil is divided into four different groups based on their infiltration properties. If higher infiltration group A, B, C, and D has the least infiltration property, like clay has the least infiltration property, so it is D. And based on there are some methods. So land is land cover, you have properties, and you have the this hydrologic soil group. You combine it, then we will get some value. That is the curve number value. So this is the concept. All these things you can read on the slides. So same thing, the calibration means adjustment of model parameters. I am giving you the example of curve number. There are a lot of parameters available, but for that we have to study the manuals and all. And why we need calibration? Same. I will not go. So there are two different types of calibration. One is a manual calibration and another one is an automatic calibration. In manual calibration, we have to change the parameters manually every time and check the result. So I have changed that curve number value, then I will run the model, then again I will see whether it is getting closer to not. And then in automatic calibration, there are some algorithms involved. There are and we can choose the parameters. But however, this is actually automatic calibration is also a combination of both, because we will give the algorithm you some objective function, but you also have to see manually whether that particular range, whatever it is giving, whether this range is feasible or not for that particular. It should not be like that I am giving a parameter, it is giving a very good result, but maybe that particular parameter is not a feasible range. So that also we have to check. Then objective function is, what is objective function? See how we will calibrate a model in automatic auto calibration. There are some objective functions like say for example sum of squared error. So I am getting the model result. I have the observed data. This is a simple example, the sum of squared. So subtract it, square it, sum it. Now what should be our objective for calibration? The error should be maximized or minimized? Minimized. So that is our objective function, to minimize something or sometimes to maximize something. Like some other parameters, other functions are there for which we have to maximize the value. Like one is your R square. This is coefficient of determination. So close to 1 is good. If it is less than 0.5, it is average. So we will try to maximize that objective function. So these are the things. So these are different algorithms available for HEC HMS. These are the two algorithms available, simplex and univariate. So for other hydrological models, you can get all these algorithms. Like SUFI 2, this is available in SWAP. So we have to select this already, then it is okay. So see, this is the uncalibrated model. So blue line is the observed runoff, the peak runoff, and this is the model simulated. So we can see the difference. Now our objective is to minimize this difference. So this is the calibrated one. So we did some parameterization and finally we reach up to then auto calibration. Actually in HEC HMS you can do both manual as well as automatic calibration. So auto calibration option is also there in HEC HMS. Then actually calibrating a continuous model is much more difficult, much more complicated than calibrating a event based model, because you see if only 1 year data is available, you can at least see the peaks and how it is varying. But say for 70 years of data, it's getting very difficult to visually interpret whether the model is good or not. For that, we have to take the statistics into consideration to make it accurate. Then, so these are the strategy. Then for HEC HMS calibration, so this basin, there are parameters available for sub-basin, reaches as well as reservoirs. And then meteorological model parameters like snow melt, evapotranspiration. So all these we can play with those parameters to calibrate the model. So calibration process is first you initial parameter estimate. Initially for while we are simulating the model, we will give some parameters. Okay, then in calibration we will adjust the parameters and assessment of agreement. We will adjust the parameter and we will check the accuracy. And we have to iterate between these two processes 2 and 3 maybe several times. I am doing something, no it is not coming. Sometimes maybe bad result can give with the parameter estimation. So we have to check all this and iterate the process to get the result, and then finally we have to validate the model. That means for one particular time period I am calibrating the model. Okay, now these parameters are okay for this particular model, and then say I have data from 1990 to 2020. Then for major parts like 1990 to 2010, like that, I will use that data for calibration. I will calibrate the model, will estimate the parameters. Then after that, for the rest of the time period, I will validate the model. Now I will not change the parameters. I have already fixed those parameters for one time period. Now I will see is it working for the rest of the time period, okay or not. Then if it is okay, then so calibration and validation, these two things are important. Adjustment of parameters, if you have available data, then we will calibrate from upstream to downstream. However, in our case we will calibrate only at the outlet because only one data we are having. Then validation I have explained. Okay, setting initial fine. So again the example, pre-calibration and post-calibration. These are the processes for model calibrating the model. So for event calibration, you have to focus on the peak, timing, volume for event. And for continuous calibration, we have to focus on volume, performance metrics as well as flow frequency. And I have mentioned about so I have mentioned there are statistics involved to check, like this is one coefficient of determination is 1. We have to maximize R square. If I select R square as the objective function, we have to maximize it. NSE is one more important. We have to maximize NSE. This is Nash-Sutcliffe efficiency. Then root mean square error. We have to minimize the error. So these are some statistics available for during calibration. Then percent bias is another statistics. So we can see that if we are using daily and weekly, then how we can define if R square value lies between 0.65 to 1, it's a very good. Then NSC R square. So these are the ranges. If we are using the daily and weekly, if we are simulating the model monthly simulation, then these are the ranges where we can understand if we are getting the R square value between more than 0.75, then it's a very good model. And so this is the one. Here we can see some model is there. We have calibrated and validated, and finally we have found the Nash-Sutcliffe efficiency as 0.88, and it comes under the very good category. So this is all. Thank you. So I will be giving you the presentation. You can go through it. Different methods are there, different all these things, and you also have to study the manual because it's not possible for us to explain everything. Otherwise, already you are getting bored, I think. So now let's go for tea, and after that we will start the hands-on session. हो गया सबका?
डिस्कशन तो हो गया, जितना भी चलेगा
चाय पी लेते हैं।